Thank you. Thank you for the introduction. And I would like to thank Manakula Vinayagar College for giving me this opportunity. And also, I would like to thank Dr. Bakinisha for inviting me to deliver this lecture. And is my screen visible, ma'am, and my voice audible?
Yes, ma'am, everything is fine.
Okay, thank you. So today we will be starting with the most transformative topic, that is additive manufacturing and food technology, which is going to take our food technology to the next level. So in this lecture, I will give just an overview of how our food technology is evolving, right from 3D printing to 8D food printing. So this is what we are going to see in our in my lecture today. So before going into 3D printing, first we will see a history about this additive manufacturing. So previously there was two manufacturing techniques. One was additive manufacturing and another was subtractive manufacturing. So people were what they were doing before doing this additive manufacturing, they were doing the subtractive manufacturing. That is nothing but they will take a block of product and they are going to carve the product of desirable designs. So that was subtractive manufacturing. So that will remove the extra materials simply. So from that, this additive manufacturing also got evolved. Additive manufacturing is nothing but we are going to control the flow of the product so that it can build up into a desired shape which we require. So this subtractive manufacturing, it got a lot of wastages, but to combat this, we had this additive manufacturing, which has the advantage of reducing the wastage of the food materials. So this is how this additive manufacturing came into picture. So this additive manufacturing, it shifted our entire food technology to the next level. So this is nothing but a layer by layer creation of a personalized or complex food structure with a digital control. So the major characteristics of this additive manufacturing is that first thing is layer by layer construction, which has the precision material, that is the material which you want to deposit over any platform. So this is a layer by layer construction. Then the main component is the digital control. So this digital control, usually they are using a software like CAD, where you will design some pictures there that can be printed into your platform. So next characteristics is that now they have moved on from 3D to 8D printing. So in the upcoming slides, we will see what are these. So the main applications of this additive manufacturing is that one is food security. The main thing is that personalized nutrition, so that we can print the materials which is needed for definite group of people, like people with diabetes and children, athletes. So these kind of nutrition can be printed. So that is the personalized nutrition, and also it has the sustainable goals along with the supply chain optimization. So these are the learning objectives which we will be seeing in today's lecture. So first thing is that we will understand what is the principles of additive manufacturing. Then next we will differentiate between each technologies, that is from 3D to 8D printing. Then we will also analyze the technological capabilities and some of the limitations of each printing techniques, and we will evaluate the application and potential benefits. So next is we will also assess the challenges and some of the future prospects of these multi-dimensional food printing. Then we will also find some solutions for the specific food printing. So starting from 3D food printing, so the fundamental of 3D food printing, as I said earlier, it is a three-dimensional layer by layer deposition with the help of a digital control. That is, we have to use some CAD or some software to design our food structure, so that that can be deposited onto a platform, and we will build the material layer by layer. So this was there in other applications. This 3D food printing came into food technology recently, very recently. Still, this technology, though we are having a lot of researchers, this is still at the research level. But in some countries like Canada and US, they have established this 3D food printing as as a industrial level. They have they have upscaled it to the industrial level. Even some companies, they are manufacturing 3D food printed products and they are commercializing it. It has gone to that level. So we have, if the students or whoever is interested in this area, so they can continue their research in the 3D food printing. So because this is the very blooming industry, very blooming research topic. So if some students or someone is interested, they can take up this work to the next level. So the basics of this 3D food printing is that nothing but these are some of the mechanisms, like one is extrusion based printing, binder jet printing, and selective laser sintering. So extrusion based printing is nothing but we are going to use an extruder. I hope you all are aware of this simple extrusion system. So in the upcoming slides, we will have some photographs of this extrusion printing so that you can understand it better. So this is how the extrusion printing technique works. So the right side, you can see the diagram of an extrusion printing. It's similar, exactly similar to the extruder. It will have a barrel like structure. So that is the compartment, and inside the compartment, you will have some screw structures. There are two types of force applications where it can be either mechanical or pneumatical. So mechanical is nothing but it is a screw based extrusion system where we are going to use a small screw shaped structure and we are going to push the food particles through the barrel. Next one is the pneumatic system. This is nothing but the pressure is given using a air pressure driven system or a pneumatic system. So this is only the method of force application varies, but uh, uh, both are in the extrusion system. So the important thing to note here is that we can use the viscoelastic paste like materials, so that whichever is having the shear thinning effect, whichever food particles which is having the shear thinning rheological properties, like if we increase the pressure, their viscosity will change. So those kinds of food materials can be used in this 3D food printing technique, this extrusion based system. So the nozzle size, it will range between zero point 0.2 to 1.5 mm. So this will be depositing in layer by layer. So next method is that one is inkjet printing, and next is binder jetting. Inkjet printing is nothing but it deposits a small picoliter sized droplets. This is applied for mostly low viscosity liquid, like your chocolate, uh, what is the chocolate syrup, like that you can use. Here, what it will do is that it will create a small pico sized droplets, small droplets over a bed, so that these droplets, over the same droplets, another droplet will be deposited, so that you can create a layer by layer structure. So this is how this inkjet printing is going to work. So the main application is that the flavor, coloring, and microdosing of nutrients can be used for this type of inkjet printing. So the advantage is that it has a high resolution, it has it is more precise, and it is also a non-contact deposition. When compared to the previous one, like extrusion type, this is a non-contact deposition. So the limitation is that it is not as structurally having the strong building capacity when compared to the extrusion system. This is having a quite low mechanical strength. So that is one of the limitation here. But if you want to deliver your flavor or coloring or your nutrients very effectively, then you can choose this type of printing method. So next one is that binder jet printing. This is also similar to the inkjet printing, but the difference here is that you are going to deposit the layers of your bio ink over a powder bed. So your powder will be coated onto each droplets, so that and one more there will be a leveler, so that will run through the bed and it will make a layer. So again your droplets will be dropped over the powder bed, and again the leveler will level the layer. So this is how it is going to build the your food product. So the advantage here is it has high speed and it can be used for complex internal structures, and also it has a multi-material capability. So the limitation is that it requires a post-processing. That is, if we are going to deposit one layer, then that requires a drying process. Then next layer will be there. So this is how this is designed. So in this picture, you can see overall comparison of each printing process: the extrusion based, binder jet printing, and inkjet printing. The selective laser sintering, this is another one method, which is nothing but it is like you can imagine it like a soldering method. Like if you have seen the soldering, how it will work is that it will melt certain particles and it will fuse the particles together. For example, here it will melt the sugar or protein particle and it will fuse the particles together, and then it will leave some time for the roller to level the layer, and then again it will do the same process. So it is having a focused laser beam, so that will make the particles to melt and fuse together. So this is how this selective laser sintering will work. So coming to the applications, so these are some of the printable materials you can use. For example, hydrocolloids, proteins, carbohydrates, and also oleogels. So these are the basic material which are printable. We cannot print everything. We cannot print all the materials. If you want to print the material, then you have to use certain combination of other materials like hydrocolloids, proteins, carbohydrates, and oleogels. These can be combined with that material to make your product printable. So these are some of the applications you can see. We have seen different printing methods. So for each printing methods, these are the some of the applications of food. So in every method, every product cannot be printed. For example, if selected laser sintering method is chosen, then only sugar can be printed using that. So there are certain limitations like that. So the wide application is that we can use for personalized nutrition, medical nutrition, for culinary arts, and also for space foods. So here, this gives the detailed explanation of the formulation which we are usually using for the 3D printing. First, the best ink formulation is the polysaccharide. It's nothing but this polysaccharide is having an excellent property which can print the food material. Preferred materials are hydrogels and alginates. So they have some mechanism that can cross link with the certain products like calcium chloride, so that they can set the shape instantly. So apart from this structural matrices, we have modifiers and stabilizers. Even though if we are having some products to give the structure, we have to have some stabilizer to stabilize the material. So that is what this xanthan gum and CNC it will give. And apart from this, we are also having the protein matrices. For example, whey protein, soy protein, pea protein isolate. So these are some of the protein matrices which can be used. And also the emulsion ink. Now there are some fat droplets which can be combined with the polysaccharide matrix or protein matrix to stabilize the structure. So see, these are called the food inks. For example, if in a pen we are using ink, right? So similar to that, 3D food printing are having some inks which are these alginates, xanthan gum, proteins, and emulsion. So these are the inks which are used by the food printer to print the food. So moving to the next level of food printing, that is 4D printing. So the fourth dimension is nothing but the time. So these are the mechanisms or response to which the 3D food printed material will change its shape to according to the temperature, moisture, pH, and time. So temperature, some of the gelatin based materials that can change the shape when heated, and moisture, like some of the hygroscopic material, they can absorb the moisture and they can either swell or contract with the water. So according to the pH response also, the materials can change whether it is acidic or alkaline conditions. And some are time dependent, like some enzymatic reaction which is base, which can change based on the time. So you can imagine this like your puppets. But your puppet, when you are frying it in oil, it will expand, it will change the shape, but it won't be in a definitive direction. But the only difference here is that your dimension change, it will be controlled, and it will be in response to the time which you decide. So that is how this is going to differentiate your normal puppet and this 4D printing. So some of the application is that self-assembling pasta and temperature activated flavor. So this is one of the interesting area where your flavors can be activated at certain temperatures. Even if your mouth, it is having a certain temperature, even if you're drinking a hot drink or something, your mouth will change the temperature according to your digestive system. Usually it is around 37 degrees Celsius. Even if it is hot, even if your food is hot or cold, your mouth will change the environment accordingly. It change the temperature accordingly. Only then it will send your food inside. So when the temperature is like for example, if you are fixing the temperature is at 37 degrees Celsius, so at that time the flavor can be activated. So that is how this 4D printing works. And the other application is the expanding snacks. So moving to the next level, that is 5D printing. So so far we saw 3D printing, it is a layer by layer deposition. 4D printing, it is the time aspect comes into picture. In case of 5D printing,
Priya, ma'am?
Voice is not coming, ma'am.
Hello.
We are unable to hear anything and screen is also not working. Please have a look on it.
Yes, sir, we are looking on it.
No, ma'am.
Ma'am, am I audible?
Yes, you're audible.
Is my screen visible?
No,
No.
please share it again.
Okay. Now, ma'am?
Yes. Yes, now your screen is visible.
Okay, thank you. Sorry about that interruption. I had a power shutdown here. So
Okay, it's okay. Carry.
So we will continue with the 5D printing.
Yes.
So the 5D printing, in addition to the 3 axes of the 3D printing, we are going to have 2 more extra coordinates. That is nothing but X, Y, Z, A and B. So that we can have a definitive curved layer deposition in addition to the 4D printed product. So the application of this 5D printing is that you can print honeycomb patterns efficiently and other biomimetics design, which are very complex. So that can be printed using this. And in this case of 5D food printing, you are having structural optimization benefits. Like you can build a product with the improved mechanical properties. You can have a very rigid structure. And also you can decide your product whether it can have a soft or a rigid structure. That can be decided by you. So that is not going to affect the output. So it has a reduced material waste, and it is going to have an enhanced surface quality, and also the printing speed will be faster. So moving on to the next level is that 6D food printing. 6D food printing is nothing but, in addition to all these, along with the 5D food printing, there is a sensory integration. So you can have your taste mapping, like if you're having a food material, so that you can have different layers of flavor and taste at different depositions. Like one layer you can have a spicy note, and then the next layer you can have a sweet note, and in the next layer you can have umami note. So it can be like that. You can modulate your product in such a way that it has a different taste and also aroma. In addition to that, you can have a texture gradient also. Like for example, you can have a hard layer, and next you can have a crunchy layer, then you can have a fat layer, so that you can decide your layers accordingly. So this is how this 6D printing works. So these are some of the technologies which can be used for printing your food material as a 60 food. That is micro encapsulation, nano encapsulation, a multi-layer system for your sequential release of components. Then next is targeted delivery. This targeted delivery is nothing but, it's like, for example, if you're taking a medicine, your medicine will not release its materials or its components in the mouth. It will go inside the gastric phase, and it will survive the entire environment. Only then it will release. Likewise, the food particle also can be tailored in such a way that we can release the particular nutrient either at gastric level or at the intestinal level. So that can be decided by you. This is possible by this 6D food printing. So apart from this, we have the applications like micronutrient fortification, and for the people those who are having dietary restrictions, and medical nutrition therapy. For these kinds of things, we can use this 6D food printing. And some more applications, like we discussed earlier, we can use it for diabetic friendly desserts, because in case of diabetes, this glucose management is very important, so that your glucose spike has to be controlled in a timely manner. So that can be achieved using this 6D food printing. And also for nutrition for elderly population, which can have a good texture and taste, as well as it can give a good nutrition without affecting their health. So that can be done using this 6D food printing. And also other thing is that athletic performance food. For example, you can have a fixed amount of protein, carbohydrate, and fat ratios. So you can formulate your product accordingly using this method. So next is 7D food printing. This 7D and 8D food printing, they are still in the theoretical level. Like we have not, we are trying to do it, but still it is in the theoretical level. It has not come into that application, but sooner it will be into the market. I hope so. So the 7D food printing, it is nothing but it has the biological integration. Biological integration is nothing but the prebiotics, probiotics, those kinds of beneficial bacteria that can be embedded into the food matrix. For example, some enzymes that can also be embedded into the food matrix, some live cells, this probiotics, which are live cells that are incorporated into the food printing. In 3D printing, you cannot do that. You can do that, but in the temperature, at the high temperature, some of the organisms are going to get killed, obviously. So in this 7D food printing, we are going to rule out all these, and we are going to incorporate the live cells, which are especially the beneficial bacteria that can be good for your gut. So nowadays we are always talking about the gut bacteria, the gut food. So this 7D food printing, it is integrating your biology, that is your living cells and this beneficial bacteria into the food. So this is the 7D food printing. The applications are in cultured meat, and also the another thing is that this 7D food printing, it is good in reducing the like we have to formulate food that can reduce the carbon footprint. It will increase the usage, it will decrease the usage of water, and it will minimize the waste, and it will uh, reduce the energy wastages. So that we have to decide that while printing our food, we have to also follow this environmental optimization and also circular economy integration. We have to follow this. Only then this 7D food printing will be a integrated one. In addition to biological and living integration, we also should have the sustainability and circular economy. Only then we can call the printed food as a 7D printing. So moving on to the 8D food printing, again, nowadays we are talking about this AI and bots, chat bots, and that thing is coming into integration in the 8D food printing. So this gives the entire complete ecosystem integration. So for example, if your machine, if you're having a personalized robo or a machine, it will read you and it will say that your vitamin D is low, so that I will print a snack for you with a vitamin for to manage the vitamin D. So that is how our future food technology is going to evolve. So it can read the behavioral pattern, and it can recognize your eating habits, and according to that it can print the food. So that is 8D food printing. Again, this is a theoretical one, and it is going to come into action, no doubt in that, but at this stage it is in a theoretical one. So this is going to have a real-time adaptation, and also you can manufacture some smart foods using you might have heard about the smart kitchen, smart gadgets, and likewise you can prepare the smart food like customized nutrition, some live cell integration. So likewise, this 8D food printing, it works. So this is the application for all of the food printing, right, from 3D to 8D. So you can have a space food at extreme environments, so that you can print your food which has a compact. For example, if you are going to design a food for astronauts, then you have to have the food in a compact storage, and it should have a long shelf life, and it should also have the psychological benefits. So when it comes to the psychological benefits, then this AI food printing comes into picture, so that it can learn your consuming pattern. And also when your gravity is changing, according to that your psychology also change, and your food habits also will change. So according to that it can print the food. So that is how this is going to get applied. also in some military operation emergency situations. So here we are going to use this food printing so that you are going to have a nutritional dense food in case when you are going for a emergency situation, so that if you are taking a small quantity, then your stomach is full. So it is going to be like that. And apart from this, you are having the restaurant and culinary industry, where you can have a personalized dining and molecular gastronomy, that fancy designs, and along with the beneficial nutrition that can be done using this additive manufacturing techniques. So these are some of the benefits. So first benefit is that as we all know, the customization and personalization is possible using this additive manufacturing, and sustainability, obviously waste reduction is there, and it is going to be economic and operational based on the demand, and the quality and market differentiation is there, obviously, when compared to other food technology. So when this new thing is evolving, there are going to be the challenges and barrier. So these are some of the challenges. Apart from this, there are many challenges. So right now we are seeing the major challenges. First thing is the technical challenges. Your material property has a lot of limitation. Every material cannot be printed. So you have to optimize your material accordingly so that it is going to be printable. So printing speed will be a concern, and the resolution will be a concern. And when you are going to go for this higher level printability, like 8D printing, 7D printing, there are going to be a lot of technical challenges. And also economic challenge. Yes, this is going to be a very expensive technique. It is going to cost your equipment high, and it's going to cost high maintenance. So that is another challenge. And regulatory and safety, still, since this is a nascent technology, you have to get qualities standards for your food product before you are going to market this product. And consumer acceptance. For example, some foods, if we are looking in that shape and that texture only, then we will be able to consume it. So if we are printing that food in a different form, that we won't have that acceptance. So that is going to be another challenge. So these are some of the future trends and research priorities. So next generation technology will be nanoscale printing for molecular level. Even you can control the food materials at the molecular level. And high printing speed, you have to research on this. And multi-material system and in situ processing and robotic integration is another next generation technology. Then your smart material development, you can program your food materials with the demand. Based on the demand, you can program your food materials. And self-healing food structures, when you are frying the product, it should be able to heal itself. So it's going to be like that. And adaptive nutrition based on each group of people. And also interactive food that comes into that integrates with the 8D food printing. And when we see the market projection, it is going to be about 50% of CAGR at 2030. I'm speaking about all these additive manufacturing, entire additive manufacturing. So this is the conclusion and key takeaways. This is a very good technological development in our food science. And if we are going to get a good regulatory framework for this type of food, then we are going to design good novel food ingredients. And also this is also going to integrate the sustainability. And the final thing is that this AI and biotechnology convergence is the very important, so that the food product which we consume can also give the gut benefits. So thank you. Thank you for giving me this opportunity. If you have any questions, I'm open to the session.
Good evening, ma'am. So, in case of any waste of these food, does that require any other waste disposal method, or it can be disposed in a normal way itself?
Waste disposal methods. Yeah, if you are going to dispose a starch material, then how you will be doing? Just like that, it's going to be, because we are going to use the food system only. If we are using some starch material, for example, if you are using a dough and you are going to waste, like you are going to throw off some dough, the same waste disposal method is going to be here also.
Okay, ma'am. Thank you.
Yes.
Good evening, ma'am. Since you said there is a difficulties in material selecting for 3D foot printing, what kind of materials are currently been using, and what are the future investments that you can like future materials that can be is on the development?
So when coming into material, so far the research is going on in the starch only, major starch and then proteins. We are at that stage only. Even the oleogels we are not able to print. So, but it is not impossible. We can do that, but we have to combine it with some other materials like hydrocolloids. So in order to print, but that is, the benefits are going to be large. So when it comes to materials. When we are selecting the material, it should not clog the nozzle of the 3D printer. And also it should have the shape stability so that you can deposit layer by layer. So these are some of the constraints when you are going to select a material. So did I answer your question?
Yes, ma'am. Thank you.
Okay, thank you.
Ma'am, in one of the disadvantages that you mentioned, it was given that contamination is possible. The whole process is machinated. How can contamination occur in that, ma'am?
When we are going to integrate the biological system, at that time we have to take the what is that contamination into account, right? Because we are going to incorporate some living cells into the food system, so that we have to design our entire food printing in an aseptic environment. We have to take steps so that it is not going to get contaminated. Even it doesn't need any living creatures, but even if we are printing normally, when we are printing one layer, that layer is going to be dried, and then we are going to print the next layer. During that, the air environment, we have to keep it in an aseptic environment, so that the contamination risk can be reduced. It is not that it is going to be it is going to contaminate everything. We have to take that thing into picture. Any other questions?
Participants, any other question? Okay. Okay. Now, may I invite Ms. Meenakshi to propose vote of thanks?
Thank you, ma'am. So as we come to the conclusion of today's session, I sincerely hope that the deliberation has been informative and intellectually enriching for all the participants. On behalf of organizing committee, I extend a heartfelt gratitude to our esteemed resource person, Dr. Priyadharshini SR, Assistant Professor, for sharing a valuable insight and expertise with us today. I also thank all the participants for their active participation and keen interest, which greatly contributed to the success of this session. We look forward to your continued support and participation in our forthcoming sessions. With this, we formally conclude today's session of the Professional Development Program. Thank you for all for joining today. Thank you.
Thank you so much, Priya ma'am. You accepted our
Thank you, ma'am. Thank you for giving
yeah.
this
Thank you
opportunity.
so much. It was a very nice session. Thank you.
Thank you.
Ma'am,
Thank you.
ma'am, Dr. Priya, ma'am, on
Yes.
behalf of MIT, I thank you a lot because you have accepted our invitation at the last minute. So we have to thank you a lot for accepting our invitation, ma'am. Thank you.
Thank you, sir. Thank you so much for giving this opportunity.
Thanks, ma'am. Thanks.
Thank you,
Thank you
sir.
so much. Oh, thank you, ma'am. Thank you all.
Thank you all.